And now it's my great pleasure to introduce Ben. So, I mean, Ben Shneiderman needs no introduction. When he sent me, he's also, I'm biased, he's a great friend of mine. When he sent me his short bio, I was a little bit kind of surprised with his short bio. He mentions his appointments. I mean, he's professor of computer science at the University of Maryland with affiliate appointments in a number of other departments, including the Institute for Advanced Computer Studies and the iSchool. He mentions some of, he's a fellow of all the societies related to his field, and then in passing he mentions that he's a member of the National Academy of Engineering, and then he lists some of the books that he authored or co-authored, most of which have had a lot of impact. To me, that was a little bit disappointing because Ben was one of the founders of the field of human-computer interactions. When he started talking about human-computer interactions, nobody else in the world really was thinking along these lines. Ben is a pioneer in information visualization. He developed a number of technologies that are widely used both in academia and in industry. Ben, I mean, I don't know what else to say. Ben, if you think about now, we all use the internet and we have these hyperlinks. We click on these links. Before the internet was conceived, Ben had this thing called hypertext, which is exactly the idea of these hyperlinks. I can go on and on about Ben, but there is also another thing that I know very well about Ben, which is very special about Ben, namely, whenever he does research, he thinks about societal needs. What is it that can help society, can help people? You know, I've known him for a long time, and this is an unbelievable characteristic of him. He's not trying to just do research to publish and move up in the ranks or be visible. He always thinks about the people and society. So it's with great pleasure that I invite Ben to give his presentation, which is entitled Information Visualization for Knowledge Discovery, Exploration Tools for Socio-Environmental Systems.
Thank you, Joseph. Appreciate it. All right. Now I have a lot to live up to, huh? Good morning. I'm very pleased to be here. I feel a little far away, so I'm going to sort of come down. I'm really impressed by this. And when Joseph invited me, and I had heard Martha Palmer speak about C-Sync, right? Sussing. All right, I'll try. And I was really impressed and inspired by its admirable goals. Especially the interdisciplinary nature of it, and the term socio-environmental certainly caught my attention. And you can see my background is in computer science and database and file design, optimization techniques, and the standard computer science. But I've come over my career, as Joseph alluded, 20% of an experimental psychologist in trying to study the way people use technology so as to improve it. And I'll mention some of those things, but and lately I've become, let's say, I would say 5% of a sociologist to try to understand social media and its impact, how to use that effectively. But the pleasure I've had in the work I've done is the crossovers to other disciplines, what I've learned from graphic designers, what I've learned from biologists, what I've learned from physicists, from humanities, and so I consider myself dangerously eclectic. But I would say that gives me some advantage. So I'm humbled by coming to this crowd because it's a new territory for me. So I'm a little curious, and you can raise your hand more than once. How many people identify themselves as computer scientists? Just a small fraction. As population experts, demographers, geographers, all right, land use experts, urban designers. What else? Architects? We have architects. Linguists. What other disciplines? Sociologists?
Sociology, social science.
Social science.
Ecology.
Ecology. Ecology. Okay, what did I miss? What else?
Conservation.
Conservation, thank you. Health. Great. No, I find that inspiring, and I'm honored to have this opening talk. and I hope to leave you with some idea about visualization strategies that you might use. And I was, as I looked at the list, I'm also inspired by the distances people traveled, not only from around this country, but from Europe and Australia. So thank you for coming, and let me try to feel a little far away from you, but we'll try to do that. I guess the way to identify myself, I found in making my title slide, probably what you need to know is my Twitter handle, because that's the way the world works, that's the way the social context spread, and that's the way you'll hear about what I'm up to. I'm pleased to represent the University of Maryland's Human-Computer Interaction Lab, now celebrated its 29th anniversary, getting ready for Big 3-0. And we're an interdisciplinary bunch that is owned jointly by computer science and the College of Information Studies, but with participants from psychology, sociology, political science, and the wonderfully titled Maryland Institute for Technology in the Humanities, MITH. Plus many other groups that we go to. If you go to our website, which I had up before, you'll find 650 papers, 200 videos, 40 pieces of software, and so on. I hope some of you at least know me from my sort of major book, Designing the User Interface, the first edition in 1986, and the fifth edition the past year with Catherine Plaisant, who's been my collaborator for 25 years. May you all be so fortunate to have a good collaborator like Catherine Plaisant, and as well a colleague like Joseph Jaja, who was director of UMIAX for many years, and a great supporter of this kind of interdisciplinary thinking. It's natural that he would gravitate to be part of SUSINC. And I worked with Joseph on NASA-supported Landsat data image management, and so we came to appreciate each other's abilities. So this book tries to tell the story about how to design technologies that work together. And the term human-computer interaction is actually growing quite old by now, in that many people, or some of the younger scientists, want to see it as sort of, well, it's just one person and one computer, but that's no longer the way it works. We're really a social environment, and in fact, I really wanted to change the title to human social interaction, because I think we have to understand the world in a social way, and we have to understand science in a collaborative way, and citizen science and all the new ways that science is going. If we have time at the end, we'll talk more about it, but about the new kinds of science that I think SUSINC represents very effectively. The book's fifth edition is distinguished by a much expanded section on social media and whole chapters now on search and visualization. But today's focus is more narrow, about information visualization. This is my work increasingly over the last 2 decades, and this book in now 1999, still a popular book, contained 47 of the leading papers from very disparate sources. Plus, we wrote 60,000 words that tried to characterize why visualization was an effective way of seeing the world. And I like to think of it as kind of special glasses. It took me quite a while to find out how many computer scientists and demographers and ecologists there were in the room, and what were the clusters and the groups and the outliers and the relative sizes of each. And what I really want is to be able to see the world through these kind of magical glasses by which I can see that and see maybe the relationships amongst you, who's co-published, who works at the same university, and trying to understand the world in these fresh ways is what this is all about. And so we have meaningful challenges here. My co-author Stu Card provided the subtitle, Using Vision to Think, which makes clear that our visual system is not merely a camera that carries data, but it's a decision-making, and it's an interpretive system by which within a few hundred milliseconds we can see patterns, groups, clusters, outliers, and gaps. And so those are the things. Our challenge as designers is to get the right use of color, size, shape, and proximity. So this remains a vibrant topic, and I guess one way to see that its health is that the business side has picked up on this. Those small university startups and little companies have gotten bought by the middle-sized companies, and the middle-sized bought the big companies. And I'm happy about the last part, which is Spotfire. And so I'm going to use this as an example, and I hope to show you enough examples here. Spotfire began from our work and published in 1994, remains one of the most highly cited papers in the CHI conference, Computer-Human Interaction. And with Chris Olberg, It was published together, and he founded the company in 1997 with a few of his friends, and it grew to 200 people and was acquired by TIBCO. And I was on the board of directors for 5 years, so I had the pleasure to see how things work in a complex way. This represents one of those rare cases where there's a single screen that shows a discovery. This is from Nick Thomas in GE Healthcare in England. I hope you can see this. It's a little small on the projector here. But basically, there's a set of sliders that let you control and filter the data. This was data about gene expression levels. And the surprising result was right over here. This red dot showed the more than expected activity of the RBP1 gene, which is mirrored here in the plate example and the 3D scattergram. And so it revealed the importance of RBP1 in the development of retinol, which in turn plays a role in embryonic development and vision. Spotfire has grown and become a very rich featured and widely used. Any Spotfire users? We have, all right, well, so there's something to learn here, but here, 27 windows lets you look at high dimensional data. And Spotfire demo gallery online, the connection here is kind of slow, otherwise I'd show this live. But you can go there and you can, begin to use it for a variety of data sets. Only one of them had anything to do with environmental, and it was this one. This one's on their World Energy Survey analysis, and if you go through it, you'll see things like this kind of now have become quite familiar. Multiple coordinated windows, a map of the world, plus some bar charts, some graphs, the tree map, which was my innovation. I'll talk more about that later. And then, various kind of graphic designs. The raw data looks like this, very familiar tabular Excel kind of display, and various ways of representing data here in a heat map, which color codes the values, thereby making it easier to find things. Okay, it's no surprise that more pixels are better. Helps you find things, and the movement is on towards 10 to 100 megapixel displays for common use for many problems. Here I put some fresh examples from one of my former students, Chris North, now at Virginia Tech, and this is a kind of standard environment for researchers looking at lots of data. And these are the kind of large wall displays. Amitabh Varshney from our group has a smaller one than that, but also shows this kind of display of information. These make a dramatic impact. They enable people to see things that would be difficult to see otherwise. There's more information. There's less interface playing around, less scrolling, less clicking, and so you can concentrate on the data. The radiologists have discovered this quite well, and I did a keynote for the Radiology Association, so I got into looking at their kind of display. So those are the examples in the medical world. And control rooms are more and more like this, these large spatial displays that are shared among groups. And that have this, which have a spatial stability, so things are in a constant position. You need only glance across to see the information that you want, and therefore your concentration remains on the content, on the knowledge domain, and on the hypothesis that you're exploring. It's also true that the visualization's becoming more common on small devices, portable devices of all kinds. I'm not sure I want my radiologist or air traffic controller to do all their work on their iPhone, but it can be helpful in many and a growing number of circumstances. Also, it's maybe no surprise that visualization has caught on famously in the media. The New York Times maybe being the best example. I've had the pleasure to work with them and help them along. But this was last week as I was collecting Ice Fridays in the New York Times about drought across the U.S. These are the so-called small multiples. I hope you can see that out there, but this year seems to be worse than almost any year since 1934, the famous drought in Dust Bowl days. And so you can quickly scan and see these images. I hope you can see that. Maybe it's a little far back for some of you, but you can see how the situation this year is really much worse than before. These infographics, as they're commonly called, provide a powerful way of communicating with a wide range of people. And I think these are great. They've gained a huge attention and publicity and huge expectations that one infographic is going to solve the world's problems and deal with water and health and so on. It's not going to be that easy, but at least there's a tremendous push for newspapers and other media to be presenting information visually. All right, what we've learned from all this, I summarize here. So, and I wrote this rather playfully in a conference keynote, and wrote it in the paper just like this, repeating it 12 times, and I playfully called it a mantra. And the notion was, give the user an overview first, see the entire space of information at once, and then allow them to zoom in on what they want, filter out what they don't want, and then click for details on demand. And each of these rows, each of these lines represented one project where we struggled for weeks and months to find the design, and that became the framing notion. This, I would say, sort of second-rate conference, Keynote, has now accumulated almost 2,000 citations in literature. And it's become very influential, many people citing it positively, some people complaining about it, offering alternatives or extensions, people making jokes about it. So it's sort of becoming a defining thing about who I am. And the reason I think it's caught on so much, because it asserts what for me is the central notion, that it is the user who gets the overview, and then the user zooms in and filters out. It's the human side, that discoveries happen from human-centered thinking. Now, of course, we also want to strongly integrate statistical methods, but it is, to me, a very central issue for me to promote the idea that human intelligence is a source of solutions. So I would say the other kind of overview I want to give you is this difference, maybe what to may be more familiar to many of you in the world of visualization, is what's often called scientific visualization. These are 3D or 2D maps. These are geographic maps, GIS systems. And they're very valuable. They have a 50-year history. It's a great success story. There's still much research to be done. But at the annual Viz Week conference this year, October in Seattle, the Scientific Visualization Conference has a declining number of submissions. And the information visualization and the visual analytics sections have a dramatically increasing number of papers being submitted. So we are seeing a change, and the InfoViz topic is only the conference goes back 18, 19 years. And I would say it's shaped around these four kinds of situations: multivariate, not just multidimensional, but multivariate data. And by that, we're talking about tabular kind of data, and the sweet spot might be 5 to 50 or 100 or maybe 200 columns of data. And we're talking about doing 1 million or 10 million rows conveniently, and 100 million or 1 billion rows with some effort. So that's the space that people are exploring. The cloud and big data movements, I was very pleased, and I take some credit for it, that the now 3-month-old announcement from the White House about the Big Data Initiative, in its 3 pages, contained the word visualization 5 times. So that's the kind of victory you look for in Washington, of the shift of the language and the inclusion of new concepts. So multivariate data is the very kind of familiar one, and Spotfire remains, I say, probably the strongest tool, but Tableau certainly gained large market share, widely used, and a low-cost tool called ClickView, the MicroStrategy Visual Insight, and many other tools are coming on strong, plus the addition of web-based tools in almost every website is presenting those visualizations. Now, those tools are different from the infographics of the New York Times. The presentation tools to explain something to other people are quite different from the exploration tools that I'm going to be showing you, which enable domain experts to explore in depth and make hypotheses
and collect evidence in support of those hypotheses. And that's a fundamental difference. So as you watch here, let's keep in mind the difference between exploration and presentation. Sure, sometimes they cross over, and part of your exploration may become a presentation. On the bottom, I list some of the many blogs that have become the popular way. These have thousands of followers. Infosthetics by the Australian and Andy Vandermoord, and Flowing Data, Nathan Yao, Infoviz.org, many others. GE's lately gotten into this, and many others. Let's see. Let me bounce back to, let me bounce back to a little more Spotfire and show you one or two things. Let's start with a simple one that my friends at Spotfire sent me. It's a simple thing that demonstrates some of the nice features, the multiple windows here, and what's called guides in Spotfire, which here provide a chance for you, if you are presenting to colleagues, to explain it. I wonder if I can get the, well, I don't want to play to increase the font, but I'll read a few. This is the initial outbreak of H1N1 in the US was slow moving, starting with a handful of cases initially, and if you click on it, it shows these few cases in weeks 1 and then week 2. There were 7 cases, and then it remained geographically isolated in the initial 4 weeks. So we click on the first 4 weeks, and we now see that there are a total of 22 cases, and then in week 6, we now have 650 cases, and then over 10,000 in week 10, and by 19 weeks we have 50,000 cases. And so you can quickly explore in this way. If you want to look at just the fatal cases, you can see where they occurred and which weeks they occurred. So this is a very simple one that sort of quite bridges the gap between, this is more of a presentation tool than it is a discovery tool, but actually it enables people to make interesting discoveries on their own, so they can select a field here and they'll see when, which weeks those cases occurred, or if they want to see where the cases were in the 19th week, you select the 19th week and you can see where they come. So this multiple coordinated windows was a central notion. And if you click on any one of them, this details on demand window will show you the details about those cases that are selected. Or if you select a bunch of them, you get a little tabular display that shows the data. Okay, can you see that well enough? Are you following along? I'm sorry that it's a bit small here, but, and you can see the data is rather modest and straightforward. So this is sort of a basic idea. One example that I like to use that I hope you'll find interesting is that I've looked at for a long time, is about 15,000 births in Washington, D.C. And I plotted I began to explore this. I plotted the age of the mother against the age of the father, or I filtered out the erroneous data. You can see there's actually quite a bunch of fathers who are 99 years old, so because we didn't have the age there. So we get rid of those, but you can see a nice linear positive relationship, the age of mothers and fathers. The oldest mother is close to 50, the oldest father is 70, the youngest mother is around 13, and the youngest father looks like about 12 or 13 as well. And so you can begin to explore these. We can look at the older ones first. And there's about 40 fields of data here. Again, it's really hard to see, but the age and race and so on. I've color-coded by the births, whether they're boys or girls, male or female, and I've sized by the weight. So the big ones are weight in grams, more than 10 pounds. I guess that's 11, 12-pound baby over there. And you can then filter out by birth weight. We can just look for the heavy babies. Do older parents have heavier or lighter babies? So if we look, we can see this dynamic filtering. And so the heavy birth weight ones seem to be uniformly distributed, right? Okay, so you can see that pattern. Or if we can look for the lightweight babies, is there a pattern there? Of course, we can make a histogram and look for those patterns as well. So it's this kind of dynamic and interactive exploration that this is designed for. Now, as I began to explore, I found these kind of interesting insights here. You can trellis by another categorical attribute. So the ethnicity or the race of the mother could be white, black, Asian, or American Indian. Remember, this is in Washington, D.C., and you can see the numbers of births, and you can see the age of the mother. And in the white community, you can see the average age of mother is about 32, 33, whereas in the black community, it's much younger, about 25 or 26. I also color-coded as to whether they were married or unmarried, and you see this early dramatic demographic difference. In the black community, the percent married is much less than in the white community. Most of the white mothers are married, very small number are unmarried. Last week's New York Times had a story about this as well, the dramatic change. This data is from mid-90s, I think, but that number has now gone up dramatically, and so there's a very strong changing demographic. So this was a kind of surprise to me that sort of leapt out as I looked at the data, and all the filtering goes on here as well. You can look at what else can we see? Oh, I know what was plurality, right. So we can look at whether they were just, these are the, we should maybe go back to the other, actually it's pretty nice. Let's go back in the other image. If we look at the single births, we see, here's the single births. If we look at the twins, we can see and then we add triplets, whoops, sorry. But we can add the triplets and see these are the triplet births. And quadruplets, I think there's just 2 pairs of quadruplets here, and maybe only 1. So you can see these quadruplets, 2 heavy babies and 2 lighter babies. Hope you can see that there. And the triplets show up. I'll go back and add them in here. And Spotfire contains a wide range of controls, so you can select the filter type. Instead of having just that, you could have a range filter. Instead of that, so we could look at a range, look at the singles and the doubles, and or just the high number births, or we could turn it into what we call an item slider, which allows you to rapidly select a single one, and we should be able to look at, come on, there we go. Those are the 2, 3, and 4 grouping. So this rapid sweeping through is one of the pleasures of the interactive exploration. I've got a few others if we have time at the end about wind power settings and other CO2 levels that we maybe should save if we can look at another time or at the end. Okay, just to sort of reinforce the power of visualization and then take some examples. This is a famous example called Anscombe's quartet. Fred Anscombe was a famous statistician, first at Princeton, then at Yale. And there are 4 sets. So this is a little audience participation part. What do you see that's interesting in these 4 sets of data? There's only 12 rows. What's interesting? Thank you.
All the 8s and 4.
Yeah, the 8s are pretty strong. That's kind of an unusual pattern with 119. What else do you see? It's hard. Even with 12 rows of data, it's really already hard to see things. But once you see them, you can't not see them. What else?
All the X, all the X column seem to be integer data.
All the X columns are integer data. Good observation. And?
X1, 2, and 3 seem to be the same.
Exactly. X1, X2, and X3 are the same. Those 3 columns are exactly the same. Okay. So those are sort of pretty powerful things that are important. That's pretty hard to tease out. But now if I took this away from you and I asked you to write down how many of those numbers, could you remember them? Could you draw a curve? Or even if I leave them up, could you tell me what they look like? You describe the relationship? Well, you might say statistics are my friend, and my data mining and statistician types say yes, but Anscombe chose these carefully, and they have the same mean and variance for X and Y, the same linear regression and correlation coefficient. Okay, so, and these 4 are not really so special. There's another 4 I could invent, or 40,000 or 40 million that would have the same properties, yet would be very different, okay? And so it's pretty hard to make sense of them, and statistics, while it's valuable, doesn't always tell you the story. But now I'm going to show you what this looks like, and in 400 milliseconds you'll know. You ready? 3, 2, 1. Okay, there they are. The first is a pretty good linear positive correlation. The second, a very strong quadratic. The third, a linear with one, what is that? An outlier, an anomaly, an error, right? I mean, we don't know, but it draws our attention. And I would say visualizations, most clear benefit is data cleaning. It finds errors in the data repeatedly, and that I get these kind of cases all the time. I had a 6,400, I don't think I have it in this set, 6,400 patient admissions in an emergency room, and it turned out 9 of those patients were 999 years old. Nobody knew, and they were doing all the statistics of the average age of those admitted, and those, and those who were sent home, and the average age of men and women, and they had no idea. I was given a year's worth of temporal data, no April. Nobody had any idea. Another simple data set of 1,400 rows, small data set, but 81 of those rows were exact duplicates of other rows, a little overambitious cutting and pasting. And I would say the majority of data sets I get have errors in them. So it really is a valuable tool only for that. Okay, and this kind of anomaly may have been just an error. It may have been, the instrument, or many other causes. And here we have yet a very different case. So these become very memorable, and if I take those away, you could probably draw them and remember what they are. And they have a meaning. We can summarize them in our mind. We have words to describe what these are about. Okay? So that's sort of a very nice argument for it, but let me go interactive and show you our early work with Time Searcher when we were looking at time series data. And this is a tool, the PhD work of Harry Hochheiser. And we were working on genomic data, but this is some stock market data, but it's readily understandable, very simple data. It's 223 stocks over 13 months. Some go up, some go down, some jiggle around. There's all kinds of patterns here, and it would take a while to explore them. But you could go through them. And so remember, the principle is overview first. So I show you an overview of all 223 at once. A bit overwhelming maybe, but still there's something you can see. So second audience question, what's interesting in the overview? Yes, in the back.
Close to the middle, there's both high peaks and deep valleys.
Yes, right. It's February. Again, I'm sorry the labels are hard to read here. But yes, there's high volatility in this data. And the way to look at that is let's grab our time box and select the peak. And what we see immediately is that every stock that rose in February fell back in March. And one interesting anomaly, Adaptive Broadband Corporation rose in January ahead of everybody else. Well, what's going on there? Were the investors especially shrewd? Did they anticipate this? Or was there something about that stock? Or was it just random variation? I mean, we don't know, but it gives us something to go searching for. We could go looking for the bottom. It's not quite as interesting, but there are some stories to tell there. But let me move on and just say what our genomic and our financial people wanted was this. Show me what started low and finished high. And do those things go up in a systematic way? Do they go steadily up, the ones that rose? Or do they jiggle around? Or was there, well, there's that February problem that threw off a bunch, but not all of the stocks, and some of them rise pretty well. Or you can create more interesting patterns, more complex patterns, like what everybody wants is a stock that goes up and that stays up. All right, so we can go hunting for those. Let's see, we can maybe make the window a little wider. So this is exploration, okay? And I can take that pattern and I can drag it along and look for different times of year for the stocks that start, low and go up for a period and then they stay up for at least 4 or 5 months. And again, our genomics and our stock market people ask us the same question. They said, this is great, but could you show us the stuff that goes the opposite way? Because they're interested in these kind of these patterns. So we said, okay, we could do that, and Harry Hochheiser built this. So we can flip it back and forth, okay? And so it's a very rapid way of testing hypotheses and going exploring for complex patterns in this very modest data set. The aspirational goal for this design was 10,000 stocks over 200 time points, and he succeeded to do that. And doing that required him to make breakthroughs in the computer science engineering as well as the interface side. The usual data structures, KD trees, quad trees, grid files, didn't work. They are fine for 4 or 5 or 6 dimensions, but when you have even as small a set as 13, but certainly with 200 dimensions, and that's what each time period is, you need to do other techniques, and rapid linear sweeps became the way to do this problem, and that's similarly what we had discovered with Spotfire and has now become a standard technique. So these all run in the high-speed store. Any question about this? This is free to download from our website and gives you an idea of this rapid exploration with, this feedback to allow users to explore and to filter in very novel ways. Okay? All right. Let me go back. Chevron Texaco came by and they said, well, 200 time points is good, but, we collect data from our oil wells at the top and the middle and the bottom, the pressure and the temperature, every 10 seconds for a year, and we've never seen our data. And so we got pushed to do at least 10,000, and we did more than that. Remember, your screen width is usually only about 1,000 pixels, so getting 10,000 on the screen was yet another challenge. Here you're looking at weather data over a 5-year period, and this is sunlight, and so you can see the seasonal rise and fall of sunlight. This orange field of view box shows us the region that's expanded in the detail view. This shows 2 months of data, and in this we've selected a pattern of interest, 2 cloudy days and 7 sunny days in between. And then we're doing a search, which is now a richer one, not an exact match, but a near match. And on the bottom overview, we show you where those patterns are found in this data set. You can make the match tighter or looser to find more or fewer points that match and adjust that kind of control. So we found these to be very powerful. They expanded the range of application of our techniques, and we've had a lot of I can say good feedback. There is a Time Searcher 3.0 which does prediction based on the previous time periods, and so that takes the technology a bit further. Other forms of temporal data we call categorical data. So instead of having a value that goes up and down, you have point events, and our major application for that was electronic patient history. Here you're seeing 3 years of a patient history. These are the doctor visits, these 2 surgeries for pneumonia and knee surgery, various lab tests. You click on the sonogram, you get the details on demand. There's the fetus in the image. You click on the x-ray, you get the x-ray. You click on the EKG, you get the EKG. These are the medications and other treatments. The gray line shows today, and this patient is pregnant, forecast to be pregnant for another 2 months, been diagnosed as diabetic, received insulin, and now an increased dosage of insulin, and Lasix to counteract the side effects of that increased dosage. So this design was conceived to cover a 100-year life history with about 10,000 medical events. And here again, we succeeded to do that, and this has become part of about half of the electronic health record systems and other tools that are out there. So sometimes categorical data is really important rather than simply numeric data, and one patient's view is great, but we got excited to do 1 million patients. And so these examples of Lifelines 2, PhD work of David Wang, was a nice success story to try to take a look at 1 million patients, and we succeeded in doing that. I think, considering the time, I'm going to move on a bit and but we were able to find patterns in patient treatment that the physicians we work with at Washington Hospital Center were not able to find, because we had developed a new language for dealing with temporal event sequences. We would align by a particular event for each patient. We aligned by the date on which they received an injection of radiology contrast, and that produces unfortunate side effect for about 7% of the population, and it's monitored by looking for high creatinine levels, and those red triangles are high creatinine levels. Some of them have so many red triangles that it just makes a large section there. And we can summarize the results by looking at how soon after their radiology contrast they receive it. And so we're able to study this kind of events very effectively. We had an even further success by the PhD work of Wang. He just completed and is going to work for Twitter. It's the second of my students that's going to work for doing visualization for Twitter. And so here we're trying to show a patient history for 1 million patients at once on one screen, no scrolling needed. And I'll just sort of briefly show, I guess again it's hard for you to see, but this is the emergency room blue for arrival. All the patients arrive. 70 out of the 100 in this example go to the emergency room. About 12 go to the floor, and about 10 go to the intensive care. The most common pattern is after the emergency room, they're discharged within a few hours. Some of them wind up in the intensive care unit, and then they get sent to the floor, and then they get home a few days or a few weeks later, and some of them die. Some of them die while still in the intensive care unit. Those are the black lines there. And so we began to see the way we could collapse common patterns and show them in a novel way to represent the common patterns and the rare events. Since the averaging effect is a little bit misleading, if you cursor over this bar, you'll see that although the patients who went from arrival to emergency room and then were discharged in, on average, about 18 hours, the distribution, it has a quite long tail of those who stayed much longer. Okay? We can also take a look by aligning on the admission to the intensive care unit, which is what our physicians were particularly interested in, and you can see that about more than half of them come straight from the emergency room. About a third of them come from the green, which is the floor, and some come from the intermediate care units. And then when they leave the emergency room, many of them go to the floor and then are discharged well, but about 20% die in the intensive care unit. Our physicians were particularly interested in the pattern they call bounce back. Patient who's in the emergency room, in the intensive care unit, gets sent to the floor and then bounces back to the emergency room within 48 hours. That is a problem. It shows that they weren't being careful about the data, about the patient's health care. All right. I do want to move on to two other kind of examples about tree maps to show hierarchical data, and then a little bit about networks. The tree map idea was meant to compactly show large hierarchies. This was our example with the gene ontology, 14,000 nodes in a 23-level hierarchy. But maybe the more familiar example is the stock market map of the market, which was built by Martin Wattenberg and with me as a consultant to them. This shows about 600 stocks. The green stocks are rising, the red stocks are falling. The area indicates the market capitalization. So Microsoft was one of the biggies. And you can see there are 11 industry groups: healthcare, financial, energy, utilities, basic materials, capital goods, technology over here. This was sort of a typical mixed day, but let me show you that one. Anybody see anything interesting there? Sort of a bad day. Can you see something interesting? Thank you, in the front. All right, there's one green square. Can you see it? Over here. And it's not just a little green, it's bright green. And, you know, if you click on any one of these, you get a mountain of data, 20-year trading history, et cetera, and contemporary news. That green dot represents the A&P Trading Company, which that day had bought the Pathmark chain of grocery stores. And as a result, they were up 6% when everybody else was down. Okay, it's a pretty dramatic case. You'll have other days which are bad, and still a few more good news. And then you have these patterns that you begin to see. Here's a green day for energy, but a red day for finance and healthcare, although there's one big exception of a bright green spot in the healthcare sector. I've come to know the spatial layouts more meaningfully, and here's a pretty green day, but this red area are the gold stocks, and they trade contrary to the market. That is, the stock market's up, then gold stocks are down. And so that's a pattern I've come to understand. Okay, and I guess we've got some more. Lots of people have made versions of tree maps. This is Marcos Westcamp's news map, and I work with a company called the Hive Group, which has taken our technologies and put them to work in a commercial way with all the sliders and this rich control panel here. Spotfire has tree maps as well. I can go back and show you. And the New York Times ambitiously began to use tree maps in 2007. Here showing the car and truck sales in the US with 6 data variables shown in this rather rich graphic, which is kind of interesting. They used our software to build this graphic, but then they imported it into Adobe Illustrator so they can do all of their fix-ups and make it really pretty, add labels where they wanted, explanations, and do all kinds of extra additions. And the New York Times has been rather bold in using new research results. This is the work of a German computer scientist, Michael Balzer, who made what are called Voronoi tree maps, which have a nice organic structure and this circular kind of pattern to show the consumer price index. But I must say it's a little harder to compare the sizes of these odd-shaped regions than the rectangles. Okay, so those are the kind of problems we face. For scalability, here's a million-node tree map, which I could spend an hour talking about, but I don't have the time. I'm going to close with the last section about visual complexity, a website by Manuel Lima. This weekend I was rereading his book, which just came out, which is just a great coffee table book with beautiful images. But he shows 772 network visualization tools. So it's certainly a hot topic, but most of them are kind of a mess. They look beautiful, they're colorful, but they're not really revealing. Graduate student Adam Perrer built the social action tool, and one of the applications with the Global Terror Database at the University of Maryland, 80,000 terror events over the last 35 years. I'm going to show you something a little happier, which is Senate voting patterns, a 1-minute video. And what we're looking at are the red Republicans and blue Democrats in 2007. Every senator is connected to every other senator by an edge, by a link. The thickness or strength of the link is determined by the number of times they voted the same way. Okay, the same way. And there were 330 roll call votes that year, and the strongest closely allied senators at 303 out of 330 were Cardin and Mikulski, ironically, from the state of Maryland. And then Lautenberg and Reed and Whitehouse, Menendez and Whitehouse, the Chambliss and Isaacson, so we can look at them. We're going to throw these in and begin filtering out those who have low connectivity, 110, 120, 130, 140, 150. John McCain, who was running for president, didn't vote enough times to be connected to anybody, so he wasn't similar to anybody. And then we get this unbelievable, remarkable, too good to be true visualization, which shows Brownback also running for president, not connected over there. But there we go. I think I'll stop it about here. And what we see are the tight spheres of blue Democrats. The two independents, Lieberman and Sanders, vote with the Democrats, and the red Republicans also. And I'm sure the separation is stronger now than it was then. In the middle, we find three senators, Olympia Snowe of Maine, Arlen Specter, and Susan Collins of Maine, who often vote with the Democrats. And so they're closer to the Democratic side. And this was a kind of remarkable predictor, because 2 years later, in February 2009, the three Republicans who voted with the Democrats for the Obama stimulus package were Snowe, Specter, and Collins. Okay? So it showed very revealing things. Also on the periphery, far from the Republican side, Dodd from Connecticut, Joe Biden, John Kerry, and Obama. Okay? Far away from the Republican style of voting. So these kind of network diagrams have become valuable. There's a lot more to say about that, but I'll just pass on to our work, free to download. Node XL is the tool we've built for the last 5 years. It has 120,000 downloads, so please join us and have some fun with network visualization. You just put the network inside your inside Excel. So Ann invited Bob to a party, Bob invited Carol, Carol invited, and so on. And instead of drawing a bar chart, you get the network. Now, these networks, here's the Senate voting network, and we supply that to you. And there's Specter, Collins, and Snowe again. So you can see that pattern. And you can also download from Twitter and YouTube and Facebook and Flickr. We began to find these kind of patterns of separate communities discussing social media, for example. This was a conference in NYU. This turned out to be the sociologists in the room. These were the computer scientists, and they weren't talking to each other except for one PhD student at MIT who was the bridge for them. We've since done this in many, many other controversial topics like political ones, the red Republicans and the blue Democrats quite separate. The only bridging group is Politico, the website that both Democrats and Republicans read. This is a Twitter network about the State of the Union address. We found better and better ways. I'm going to just, I think Joseph wants me to move on. I think I've used my time, but to show you different ways you could study common discussions about environmental topics, and we studied the oil spill community, which is two very polarized groups of the climate skeptics as well as opposed to the environmental groups. And we're getting increasingly fancy in showing the groups and the relationships. This was a recent conference I attended on collective intelligence, and the groups there that were in the room and tweeting about the topic were just very clearly shown, and people were quite excited to see that I could produce this and show them that. This is economic development in the state of Pennsylvania, brought to us by Scott Dempwolf. And here's one of the beautiful but not very useful diagrams, but once we pull it apart and simplify it, we can now understand what are the drivers of economic development, which are two individuals who have about 200 patents each in pharmaceuticals. In Pittsburgh, the Westinghouse Electric Center is the main research generator, and then you have also the suburban areas of Philadelphia are key players. I think I'm going to have to cruise on, and that's the book, and that's the group. I just close with saying that the succinct goals are well aligned with what I think are really important framing notions of the UN Millennium Development Goals set out in the year 2000 to be realized by 2015, but sadly the progress on environmental sustainability, global partnership, maternal health, gender equality, and ending poverty and hunger are slow in being attained, although some success stories are in the data as well. The UN is now regathering to create a new set of goals for 2015 to be set for the year 2030. And I'd love to see this as sort of part of your agenda and the agenda of my colleagues in computer science in every discipline. I think we should put our powerful technologies to work in creating social good, pro-social projects, and make a meaningful contribution to a better world. So I'll close with that, and thank you for your attention. I'll be glad to stay and answer questions.